Okay.
And start.
Right. Afternoon, everyone. So this is a talk about something I discovered just while poking inside some of the Python internals, because I was trying to actually solve something else I discovered while researching my other talk. It's really about what happens when you hit Control-C when your program is running, particularly under Unix, because that's my expertise, and you sort of expect, oh, it's going to just shut down and exit immediately. But I discovered maybe it might not, depending on what you're doing. It's not too serious if you're just at a console and you want to kill it, because if it doesn't die, you can kill it harder and just keep killing it until it dies. But I imagine this might actually be an issue if you have some sort of automation system where where your whole system sends a sig term to your process and you expect it to catch the interrupt and sort of clean up all its database handles and write things to disk that you really want written to disk, and you actually want things to shut down when you ask them to shut down. So it all comes down to blocking system calls. So if you've ever got your gloves out and dug into what happens inside, particularly C Python, I don't really know anything about PyPy. If you have some sort of blocking system call, particularly, say, reading from a network socket, or even just saying, wait until a network connection arrives for me to process, the general pattern that happens is you drop into some C code, which drops the global interpreter lock. And that's to let other Python threads keep doing useful stuff while you're just waiting for this blocking system call. Then you make the system call, then you take the lock again to make sure you can safely call Python stuff again. And then, so with POSIX, when the system call is interrupted, you get, if a signal handler arrives during a system call, it will usually interrupt it. There's a particular error code, EINTER. And if that happens, then you go and check, did a signal handler run, did it throw an exception? So for example, by default, Control-C will the handler for that will throw a keyboard interrupt exception. So if that happened, then you bail out of that system call. Up until Python 3.4, if the handler didn't throw an exception, it would still bail out of your system call and you'd get some other exception. Python 3.5, they changed their mind and said, no, we'll actually redo your system call for you, so that every single piece of code that makes system calls doesn't have to sort of handle this interrupted error and try again. So this mostly works because if you've actually made the system call and you're sitting there waiting for something to arrive on the network or file or something and it gets interrupted, that's not a problem, it all works. Problem is there's a race condition, which is sort of in between dropping into the C code and actually starting the system call. If the signal handler arrives there, you're going to jump into the system call and there's nothing which is interrupting that system call, so it'll just sit there forever until you press Control-C again or until someone tries to connect to your server, at which point we'll immediately go, oh, now hang on, I can't talk to you, I'm being shut down. Right, so there's an alternative way to handle this, which is the other thing it does, which I didn't show on the previous slide, is in addition to all the other steps that happen in the signal handling code, is the signal handler can write a byte to a particular file descriptor. It's not done by default, but you can set a file descriptor from signal.setWakeUpFD. And what happens then is you can restructure all your code to use asynchronous I/O, and you only do one blocking system call, which is you do a select or poll or whatever it is in your operating system, and you say poll until something happens on the network or until something gets written to this file descriptor. And that way that you can guarantee that you will exit out of the system call as soon as an interrupt handler has run and written this byte. So if you want to do this, you have to restructure your code to use select and poll to wait for things to be ready and then use non-blocking I/O. And you obviously actually have to consume this byte, otherwise next time you go around it'll go, oh no, there's still a byte in there, we're going to interrupt you. That sounds like a lot of work, but the good news is, I seem to have lost a slide somewhere. This is bouncing all over the place. Okay, I'm not sure what happened to slide ordering there. But the good news is that if you use asynchronous I/O framework like Tornado or Async I/O, they both do this. I haven't looked at any of the others. I wouldn't be surprised if they do this as well. So there, if you just install a signal handler with Async I/O, signal handling mechanism, this will all just work. And when you send a sig term or something and you have a signal handler, it will reliably interrupt what you're doing. Thank you.
Okay, next up we have Vulture in Python by Philip Sterne.
my screen was flashing.
Are you outputting anything?
I should be. Where are we going to end up?
How do we get your display settings up?
And we have
Okay. So let's go. No, it's not. Control M, I guess. No, Control Command Enter. Okay, there we go. Okay, so hi everyone. I'm at Takealot. We've got a reasonably large Python code base. Some of it is already a couple years old. I dislike code in general. I want code that is not being used to go away. Otherwise, I find that it's just too confusing to try and understand what the hell's going on in this huge code base, because half the things don't get called. So I came across this pretty cool Python package, and I thought I'd tell you about it. I think it's about the right sort of thing, length of talk for a lightning talk. So for illustrative purposes, this is my massive code base spanning many Python packages, many directories, many subdirectories, etc. And when I run it, it works, right? It does what I need it to do. But I don't really like the fact that there's all this sort of bloat hiding around that I'm not entirely sure what's happening. And if I discover sort of tracing around things, how should I go about sorting this out? Well, the key thing is you just do a pip install Vulture, and then you do the magic. So okay, so when you run your program, it still works, and now you can just say Vulture on my code base, and it'll go away and it'll scan your entire code base. It will not run things, so there's some issues that come up there. It can be configured to ignore your test code. So maybe you're a very good developer, you wrote tests that reference all your methods. If you just ran it normally, it would say everything gets called, because in the test methods, they call them the things. So you can actually tell it, if this directory is called test, don't actually include that sort of stuff. And when you go and run through it, it'll pick up, actually, hang on, there are two things. So there's this function called not called, which doesn't actually get called anywhere. And here you're setting a variable called temp that doesn't actually get used. And so this was a little bit of a misdirection. I don't know if many of you picked up on the temp thing. Yeah, okay, and that's basically the sort of the easy, the vision, the dream. So if everything works really well, then that's the end of the story. Unfortunately, in our code base, we've got some unhappy things. So in some cases, we sort of say, oh, well, because Python's a dynamically loaded language, we can do things like, you know what, I just want to know about all the methods in this particular function, and then I will, in some way, figure out when I want to call them in a dynamic fashion. And this is something that Vulture doesn't quite do very well. So because Vulture makes the decision to just do a parse through all your code, it's not going to actually run the code and try and figure out what you're referring to. So in our Takealot code base, how we've used the Vulture stuff is we've ended up with a little decorator for all sorts of functions. So if it's an init method for a class, or if it's just a general function, then we've just got a little decorator that will do a bunch of logging. And we've managed to pick up some cases where things are being called dynamically, and other cases where basically there is no conceivable reference to it for the next sort of, the past 2 weeks. And so then we feel comfortable commenting it out. So be reasonably careful with this stuff. I mean, it's all in GitHub and it's all whatnot, but we're reasonably careful with that. And yeah, that's the end of, okay, and there's just a little bit of a proof saying there you run it, it actually does call the sad Vulture thing, but it thinks it's unused. Yes.
I have a question.
Yes.
If you have a function A
Yeah.
and function B calls function A,
Yeah.
but nothing else calls function A and nothing calls function B,
Yes. Then it
will
will.
Vulture pick up that function A is not called?
Yes. Yeah. So I should have gone into that more, but yeah, it does the whole sort of figuring out the call stack of everything. That does the right thing. So yeah, that's how much time do I have? Yeah.
You're down to 18 seconds.
Okay. Cool.
Okay, so next up is EDX by Carl Dawson.
I've not got any flashy slides. You may have seen on Twitter, I arrived in Joburg at 10:30 last night, got up at 6 o'clock this morning, and my car was gone. So so it was a bit of a welcome to Joburg moment. I had been warned, that was the funniest thing. I'm also not technical, so when I saw the presentation this morning, distributed pub sub infrastructure with Apache Kafka, I almost had a nosebleed. So this is going to be the opposite of a lot of the other presentations. My name's Carl. I'm the co-founder of a company called Proversity. We use the edX platform. So some of you may well know Coursera, Udacity, Udemy, and things like that. We've been programming in Django and Python since 2013, building MOOCs by employers, basically. So we work with the British Army, the Bank of England, Network Rail, Lloyds Bank, people like that, to build courses to help people when they leave school, university, and if they're changing their career halfway through their career. We're just about to move all of our technology team out to Cape Town, having done a review from Santiago to Laos, or Laos, I don't even know how to pronounce it. We did a review globally of all the best places to put our technology team. And we looked at absolutely everywhere. I'm very pleased to announce that Cape Town is going to be where we're going to be basing it all. Thank you. The beast that is edX is a very complex one that was built by Harvard and MIT. It was built with a $60 million endowment. And what's actually the benefits of that is it's a hugely fantastic thing which has a huge amount of features, but the flip side of that is it's a really difficult beast to actually work with. So the big challenge for us in the next year is to grow the tech team from 2 people in London to 20 in Cape Town, and to get the best in Django and Python programmers to look at how we actually develop out. To give you an example of the success story we've had, the Bank of England built a course for school leavers in England, which now meant that the people that got taken onto the apprenticeship this year didn't have to have any qualifications at all. They went through that course and went straight into the Bank of England. So it went from extremely kind of closed shop, where it had to be sort of friends of the family of people who worked at the Bank of England, to a total change in the way that they've actually done everything. When the managers there discovered the sort of the depth of the changes, or the degree of the changes, they were absolutely shocked in terms of, they had said, well, they need to go to this university or have this kind of person, this qualification, or know this person, and they realised that it was totally changing the way that they recruited, and people don't have to have the set qualifications that we all expect. They can teach themselves. So if you want to be part of this adventure, we are looking. Tell your friends, tell everybody. My name is Carl Dawson. You can find me on LinkedIn. And thanks very much for the opportunity.
Cool, thank you very much, Carl. Next up is AST linting by Bryn from Oracle. AST linting, is that right?
Oh, right. Yeah, there's kind of it. Hi there. Let me get my slides up before he starts counting. Is this going to work? The last unsolved problem in computer science.
The greatest and most problematic.
says best resolution. I don't want the best one. I want the one that's going to work. Yeah, that's the one you want.
That's on that resolution.
Has anyone else not got slides if they want to continue? Yeah, is there another lightning talk? It doesn't have slides.
Laura, do you want to give your talk? Yeah, let's bump you. Wait, so out of the guys who are doing lightning talks, who's doing a Carl light talk?
Okay. I did reset, or do you want to pop a power slide now? Done. We're now at the Twin Love Hubs for a minute.
Oh, okay. Well, we have a minute. Okay. Oh, I have to start entertaining. Okay, all right.
I think you're going to have to shorten the time for your speaker.
Which is appropriate. Okay. Hi, I'm Bryn. I work at Oracle in Cape Town, head up the engineering division for the Oracle Public Cloud. Also, we're hiring, obviously. But we've got a problem in that we've got a big code base. We've got, hundreds of thousands of lines of Python and Twisted is the event-driven framework, and some of this code was written when we were a startup, so it was written really, really quickly, and we're still maintaining it. And then we're hiring. So we've got, like 80 people in Santa Clara in Silicon Valley, and Silicon Valley is a very competitive area, and Oracle's not the most competitive company to work for. So we got lots of new guys, lots of guys who don't know the environment, lots of guys who, they just know Java, and now they're trying to work on a Python code base. So we get lots of problems coming up, which, since Python's a dynamic language, it only comes up once things are running. On QA sites, and our QA cycles are incredibly long. So, there are issues there, and we're trying to catch them through, basic source code analysis. We do PyFlakes, things like that. But there's some particular ones which we have problems with, and here is the first one. First, I must explain that in Twisted, you can make a generator. I hope everyone knows what a generator in Python is, and use that to do asynchronous I/O. But that means you have to yield in the generator spec every time you want to call an asynchronous function, and obviously people forget this all the time because they don't know whether they're calling an async function or if it's just a normal function. So they do that, the whole thing explodes, everything falls to crap, and our sites break. So what we've done is we've written we hacked together a quick AST checker, which goes through all the code which is committed each time we get commits. And AST is obviously an abstract syntax tree of the code in your code file. And we've got little checkers which walk that code path and then throw out these basic mistakes. So here what we did was, and this is just using the basic Python, the normal Python built-in AST. So import AST, pass the file, and then you can run a function on it. In this one, in each case, we visit each function definition. We check if it's an inline callbacks, and then check if it's got a yield in it. In this generator line. If it's not, we throw an exception. And that goes, let me just try and there we go. And, so this gets done in our check-in phase. The thing throws an error. Sorry, guys, you've made a mistake. Please go back, try again. The second one, which we see also a lot, is problem statement 2, which is I can't count very well. This is in Python specific. This is the logging library in Python, which means that whenever you interpolate into a Python line and you give the wrong number of arguments to that log line, things break, as we can see here. That's the wrong one. So everything goes to hell, and often this is only in an exception handler which never gets called during the normal checking code or the unit testing. So it gets to QA, they hit an exception, everything breaks, people start shouting. So obviously, we've again decomposed the AST and forced out a bunch of errors whenever these sort of errors are hit. The third one, which is my particular favorite, is that since we've got a very old code base and there's a bit of cargo culting going on, sometimes people think that to make a generator, you have to yield on every code path in the function. I don't know where the people got this idea, but it's fully entrenched in our code base, and I'm working hard to get rid of it. So people think, hey, I should be using inline, well, I'm in an inline callbacks, I need to yield in every code path, or it's not going to be a proper generator. So they keep on putting in this yield succeed, which all it does is it just throws the function out. It doesn't actually do anything. It's a crazy piece of code, and it annoys the hell out of me. So while it actually runs fine, if we run that, yes, I am randomly just calling all the things because I think I need to, but luckily we throw out an anti-pattern warning on that when we do check-ins as well. So the point here is that AST code linting is quite fun. It's useful for particular problems you have in large code bases spread about lots of people and people who aren't necessarily Python developers. And even when things compile or even work correctly, there are things you want to get rid of. And it's nice to catch those in check-in and get those before the unit tests start running. And the actual implementation is really simple. It's easy to walk these things. Someone here might mention that there is a Python package called Pylint, which does the same thing. But I spent a little bit of time trying to translate these across to Pylint just after writing them, and it was hell. So if you feel like playing with ASTs, it's a fun way to think about languages. Have a look at AST package in Python. Thank you.
Nicely done. So next up is Laura, and Laura is talking today about Numpy in anger. Numpy in anger.
Yeah, I just need to merge them. No, not no. I don't merge them again.
I can't bloody see it.
I know, right?
No, you do need, does need to be on.
What?
Ah. Can I turn off the bottom display?
Yeah.
Can you?
Yeah, I think. Or not. Oh.
Yes. How about we just move this to that display?
Yeah.
Where's the?
Is it up or down? I think it's up. Okay, that'll be.
That's a lot of tabs.
Okay, this is going to be very short because I just decided to do this just before now. So I work for the SKA, and we have data that consists of it's electromagnetic radiation really from space. So you collected antennas, you multiply them together. We need to correct for corrupting factors at each antenna. So each piece of data we have is a piece of data from two antennas, say antenna 1, 2, and it's corrupted by corrupting gain from both of those antennas. So we need a solver that can figure out those two numbers from this number that's comprised from both of them, like multiplied from both of them, for a range of them. So we'll have antenna 1, 2, antenna 1, 3, antenna 1, 4, and so on. We want to solve for a gain just for each antenna. So if we have 7 antennas, we'll have 7 times 7 minus 1 over 2, which is 21 bits of data, and we then have to solve for 7 gains from that. Okay, so this is the algorithm that can do that. So my task was to write this algorithm into a little bit of Python code, which I did over here. Okay, where are we? There we go. Okay, so this is the first time I wrote it literally line to line through the algorithm. And all I wanted to do was to get the right answer, so I wrote it badly using list comprehensions, and it worked, which was already amazing. So this worked amazing, but it could be a lot faster if I actually made use of NumPy, I knew. So this is taking this bit of code and NumPy-ifying it, which actually, as you can see here, sort of, is easier than you would think. Compare this line, for example, to this line. It's just a matter of using some ellipses, making sure that our antenna is on the last axis. So we have our data looks like a whole bunch of frequencies, like 1,000 frequencies, a whole bunch of timestamps that you recorded data for, then the antenna on the last axis, so, or the antenna pair on the last axis. Over here, using a bit of masking, NumPy masking over here, which we created over here. And other than that, it's pretty much the same algorithm, although it took me a long time to figure out how to do this properly. And the resulting speed up from using NumPy, the resulting speed up. Okay, so this is our visibility shape. It's 20 timestamps, 1024 frequencies, and these are the pairs of antennas. So it's just 4 times greater because we have polarizations as well. I'm just averaging it over time over there. And then using the original algorithm and the NumPy-ified version of the algorithm. And over here we get pretty much equivalent amount of timing on it, and it's because we've averaged it down, so we don't have a whole lot of NumPy dimensions in our array. Here I'm keeping the frequency, so I'm solving for one of those calibrated, the gain terms for each frequency, and this is going to take a little bit, but yeah, we can see here for almost nothing, we're getting a 5 times speed up. And that's just because you're making use of the fact that the people who wrote NumPy are much smarter than I, and it's compiled C code underneath, and you know the types are all set and so on, for really almost no effort. Well, a little bit of effort, but very little. Thank you.
Thank you very much, Laura. Okay, so next up we have How to Screw Up Loading CSVs in Python by James Saunders.
Okay. Is it going to work? That's not very many tabs. Oh, something flickered. But keep going for the. Yes.
Good Lord.
Yeah, your one's also refusing to mirror.
Okay. Okay, cool. Okay, right, let's go. So now that pretty much every company in the world wants to get on this data science thing, you're getting all these companies from reasonably unsophisticated industries like agriculture and brick making and stuff like that. They want all their data analyzed. And the way they're going to ask you to do it is by vomiting out something resembling a CSV at you. Now, in my mind, you know, this is easy. You've got the CSV standard library, and you do the CSV reader thing, and that's all great. But when it's 16 gigs of something resembling CSV, it becomes a lot harder. So the first thing is that the classic CSV reader is extremely slow. Or not. That's embarrassing. No. Thank you, Live Debugger. Okay. But then if you use pandas, like Laura says, it's a lot quicker. In fact, it's like a lot quicker, just like 5 times. And if you have date times in this, this goes to like 50 times or something. Now, the next thing you'll find with these CSVs from the wild is you would expect the whole file to be in one encoding. But no, you ask for all their data, right? So they're going to take all their data files and just cat them together and give it to you. Some in UTF-8, some in like CP1552, which I still don't know what is. So then this thing called cchardet becomes your friend, which is a probabilistic character detector. But if you use it properly, you can do this sort of hybridized, self-healing decoding. So this took about 20 lines to put together. I don't have it here, so you'll just have to trust me. But took about 2 weeks to figure out how to use. Then you're going to want to put this in some sort of database. So obviously what you do is just load it up into Python and then maybe use the pandas to SQL thing. No, because that will be exceedingly slow. Because as soon as you hit any sort of native Python type, everything is slow. You've just got to keep everything in some sort of Numpy or pandas array. So it turns out the fastest way to get a CSV through Python into a database is to load the CSV and then write another CSV in a perfect format and then use MySQL's or Postgres's native load CSV, and you'll get something like 30 times speed up. So my last thing is, if you are generating CSVs, please be good to the world. We've seen things come out of major software packages that have mixed encodings. It's just terrible. Yeah, and if you have to load CSVs, do it properly. Cheers.
Awesome. Thank you very much, James. So next up is PyQuery by Nicholas. So we've learned that Ubuntu works amazingly well and Apple Mac doesn't.
Except that we can't get mirroring. Oh, just mirroring. So this won't do the same resolution as that. And so Ubuntu just says you can't have mirroring, go away. You can probably do it with X-random, yeah.
So, PyQuery is just basically Yeah. Okay. PyQuery is just a very neat little thing that I quite like because it makes it very concise to traverse and manipulate HTML without getting into the ugly elementary and LXML stuff. So it sits on top of all of that, but it just yeah, it just makes it. If you're familiar with the jQuery idiom and you've got used to that, then this is just a very nice, easy way of quickly either reading or fiddling with HTML or XML documents. So I'll just quickly show you. You just, once you've pipped installed PyQuery, then, oops. Okay. So a very simple example. So say I've got, here's my little HTML chunk, and you instantiate this PyQuery thing, and then now, from now on, that D thing is like the dollar in jQuery. Is a lot of people familiar with jQuery? Yeah, okay, well, not so many. But and then, okay, so say I wanted to change the text of the H1 tag up there. Then I could, so you know, jQuery takes these kind of CSS selectors, and yeah, so changing the text node to that. If I now run that, whoops.
It wasn't just me.
Yeah, it's a bit awkward. Okay, there we are. All right, and there we are. Hello world now. Hello Joburg, and just these other little examples here. If I wanted to add another item to the list, I've got 1, 2, 3 up there. I'm going to add that one. And they've implemented not everything, but quite a lot of the jQuery sort of API. And iterating through elements is quite easy. I'll just show that one first. Let me just take this away. Sorry, this is a bit painful. Yeah. So, oops. I need to get the text node. So as you can see there, it actually is an elementary element underneath, but just makes it quite easy to read it out. And yeah, if we look at how I've finished the document, what it looks like now, just take this away. Then there we are with the extra element and the extra class added to the second LI. Okay, thank you very much.
Well, thank you very much, Nicholas. Last up, we have Stefano, and he's going to be talking to us about Debian Python moves kicking and screaming to Git.
If I can get my laptop to work.
Well, hopefully, you were one of the guys who made this, aren't you?
Yes, and we discovered it does not like my laptop at all.
Potential.
Hang on, I cannot type with one hand. It's just not an option. So, the Debian Python Git team manages a lot of packages. Let's say somewhere in the order of 600. Lots and lots of packages. And we have them all in one big SVN repository, because that's how you use SVN. Yes. So if we look at the Python Biggles, because that's an interesting looking name, we just keep the Debian directory in there, nothing else. Blah. Oh, it's bad. Just the Debian directory. We don't have all the upstream source that you would also have in a package. Also, we've got like 33,000 commits. So we decided to move to Git. And that was fun. And then last year at PyCon ZA, I decided it would be fun to do this while keeping all the history. Because, you know, like, I'm a reasonable programmer. I can do this. I've done SVN to Git migrations before and kept all the history. I don't see why this should be any harder. It's only 600 packages where I'm normally doing one. So I started writing some code to do it. And it looks something like, what did I do with that directory? Oh, fine. I'll find it again. There's this fantastic package called SVN fast all imports. So you might have heard of Git SVN, which lets you add a remote to your Git repository that's an SVN repository. It's not very good. It doesn't really handle tags and branches well, and it falls over many SVN merges. So if you want to properly migrate a package repository, you use this thing that the KDE people wrote called SVN fast all export. And you write some rules that are regular expressions that say, when you see a directory like that slash packages slash something slash trunk, then use that something as the name of the repository, make the branch master, and just grab all the commits into that. And you have to match every single path that you're going to get. So we've got lots of these. And you have to match even the things that you don't really want, because what the fuck are they? And yeah, somewhere here, there's some Python that generates more rules because those rules weren't enough. We run this migration thing. I'll come back to that in a minute. And we get something that looks like this. Don't know if you know git k. So you know, gets a directed acyclic graph. This is very small. Pretend you're sitting up front and you can see everything. There's a commit that's on its own. It's not attached to anything else. Oops. This history looks vaguely linear until we get here where there's this crazy octopus merge of this commit here has, is that 4 parents? I think it's 4 parents. So it turns out this is perfectly normal because in Subversion, every file can be at a different revision. And when you do a Subversion tag, you're actually just saying copy all these files to that directory over there with a special name. And if those files weren't all SVN upped first, they're all going to come from different revisions, and you get crazy shit like that when you try and turn it into Git. So during the sprints last year at PyCon ZA, Gary van der Merwe, who was a developer on Bazaar and knows a thing or two about version control systems, helped me figure out how to fix that. And you'll find a bit down here where we do that. Up a bit. Here we go. Clean SVN bulge package commits. You look at all the refs you've got. Well, you try and find the thing that looks like a tag. You see how many parents it's got, and you just pretend that they all came from the most recent parent, because chances are the person who was tagging it knew what they were doing. Then you use some low-level Git commands to create new commits and insert them into the history, and everything is great. You do that, and you end up with something like, I don't think I actually have that intermediate stage, I only have the final one, but you can pretend that we clean it up. Then, remember I just said we had the Debian directory, but there are also other files that the upstream had, things like the contents of the package, not just the packaging. So, we also want to grab those. And the way we do that is by importing every source package that was ever uploaded to the Debian archive as a commit. And if you look at this Git history, you'll see there are 2 separate branches of development. There's the upstream ones, like this commit and this one and this one. And in between, there's some Debian releases, so each upstream probably has a couple of Debian uploads. Woot! And then we've got a final cleaned up version.
Apparently I'm supposed to kick you off.
Please do that.
Okay, fantastic.
See, 3 columns, very complicated, but no octopuses.